Okay, you have learned about tree, specifically binary tree. Okay. So now we will go into tree traversal. Now, tree traversal refers to a way to navigate the tree. How you go about going from one node to another node, from one element to another element. That is tree traversal. Okay. So because it's a tree, and this one is specifically binary tree, there are certain ways to navigate this tree. And especially binary tree can solve many different type of problems. So the way you navigate the tree will determine whether the problem can be solved or not. Okay. Now, one of the things that binary tree can facilitate us is in arithmetic expression. So your binary tree can solve quite a number of this arithmetic expression problem. But before that, we need to understand what is the component inside arithmetic expression. You have operators and operands. Okay. Now, if I say A plus B, so the plus is an operator, and the operand is on the left and right side. Now, most of your operators would require two operands. Clear? And in certain cases, you also have the limiters. The limiters is some special symbol like parentheses, bracket, and those kind of thing. Okay. So normally you have what we call a binary operator because you need two operands. But it's also some unary operator. For example, if I want to say -5, so I only need to have one operand. Okay, so we call it unary operator. It doesn't need two operands. Now, the one that you are familiar with, which is this form, is also known as infix form. It is called infix because the plus is in between two operands. Infix, in between. Clear? Now, this is the one that we are familiar with. But if I were to program this, okay, I want my computer to evaluate this. I'm building a function to evaluate an expression. Now, there are many things that I need to include as well. Now, one of the things is I need to include operator priorities. You have learned in your school, if A plus B times C, we need to do B times C first, right? Then only I can plus. So you can see it is not really straightforward. Okay? You cannot just ask computer to add, divide, times. You have to tell the computer to look out for this priority as well. So you must program that it needs to do the times, divide, then only plus and minuses. Okay? So it is not so direct. Okay? And if it has a tiebreaker, meaning it's the same level, what needs to be done first? And once you teach the computer to do the times first, then you also need to tell the computer there's some exception to that. For example, if there is a parenthesis, then they need to do the plus first inside the parenthesis, then only the multiplication. Okay. So there are many rules that need to be followed if I'm using infix. Okay, normal way of solving the expression. So infix is hard to pass for the computer, meaning if I use infix expression, there's a lot of things that I need to program. Okay, the code will be a lot. But for the computer, there's an easier way to solve or to evaluate arithmetic expression, okay, by using binary tree. Now, your computer can use another form of arithmetic expression called infix and called postfix or prefix. Now, this example of postfix. Notice that in postfix, your operator is after. Remember, after is post, okay, after. So instead of A plus B, it becomes AB plus, okay. This is an example of postfix. Instead of A plus B times C, this is ABC times plus. Instead of A times B plus C, it becomes AB times C plus. Instead of all this, it becomes this. Now this form is not easy for us to solve, okay? But very easy for your computer to solve. So something is easy for us, it's not necessarily easy for the computer. Something is easy for the computer, it's not necessarily easy for us. Okay? So that's why we constantly search for algorithms that can make the processing faster for the computer, not for us. But a small problem, if I'm using this postfix, if I have an operator, it will expect the last two items before that are some operands, okay? So if I want to do like -3, then you will expect you have to do 3 minus. You will expect there are 2 operands. So if it is a unary operator, I need to replace this with special symbol. For example, like %3, 3 means -3, okay? So we use special symbol to represent unary operator. Now, how does your computer evaluate postfix? So let's say this is our expression, normal expression, the one that you're familiar with. Then we convert this, remember this is infix. So we convert infix into postfix. Clear? So we convert infix into postfix. Okay, then we can start evaluating. Now, whenever we see an operand, we push into the stack. Okay, operand push into the stack. Operand push into the stack. Next one is an operator. So when we see operator, we pop from the stack twice. Okay, so pop, then pop. Now there's nothing inside this. Clear? Okay, then we evaluate this. Okay, solve this. Now the result of this will be pushed back into the stack. So what you have is the result of this. Clear? Which is this one. Okay. Then we will continue. C, push into the stack. D, push into the stack. And then an operator. Automatically pop from the stack. Pop from the stack twice. Then evaluate this. The result of this, push back into the stack. Okay. Clear? Okay, so this is the result. Okay, next, another operator. So another operator means 2 more. pop, solve this, push back into the stack. So this is the result. Then we continue with operand F, E, and then operand F. And then another operator plus. So pop, pop. Solve this, push back into the stack. Okay, so that's the result. Last one, divide. Pop, pop. So now there's nothing inside the stack, empty. Evaluate this, then push back into the stack. Clear. So once one is ended, the value that inside the stack is the result of this expression. Okay, clear. So you can see your computer can evaluate the postfix very fast, very quick. It doesn't need to think about the operator priorities, the bracket, and this kind of thing. Okay. So that's why your computer can process prefix, postfix very fast. And that's why also in the old days, most calculator, it's no computer, most calculator use postfix or prefix evaluation. Okay, and because processing is very, very slow, so you have to use every single tricks available to make the processing faster. Okay. So when you want to add two numbers, you need to press the number, press another number, and then press plus. Then you get the result. Okay. So that's how your computer solve prefix arithmetic expression. But how do we get from this infix to postfix? So this is where tree traversal comes. Using tree traversal, I can easily convert this into postfix. Okay. So now we go into tree traversal. Now, these are most popular tree traversal methods. You have pre-order, in order, post-order, and level order. Okay, first is pre-order. Okay, pre-order traversal. Now, in pre-order, you visit the root first. Then only you visit all the children. Okay. So meaning, the first opportunity that you get, okay, when you reach the nodes, you visit the node automatically. Clear? Then you go to the left subtree. Go to the left, visit. Go to the left, visit. Go to the left, visit. There's no more left. Then you go up. But this one visited already. Then you go to the right, visit. Up, up, right, visit. Up, up, right, visit. Then go to the left, visit. Up, go to the right, visit. Go to the left, visit. Up, go to the right, visit. Done. Clear? Now this is the code. Okay, you can see the code is quite simple. Okay, you visit first, and then you call pre-order, go to the left. Notice this is the same. So it is using recursion. Okay, pre-order, pre-order. Another example. Visit, 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 up, visit, up, up, right, visit, visit, up, 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 right visit, left visit, right visit. Clear? Okay, now we go into the conversion. So using that pre-order traversal, I can get prefix form. Okay, provided that you properly put your arithmetic expression in a form of binary 3. So this why binary 3 is very important. Okay. So for example here, given A plus B times C minus D divide by E plus F. So this expression can be coded as a binary 3 into this form. Okay. So once I've coded this into this binary format, then I can easily convert this into prefix. So when I run pre-order, I will get this one first, then this, and then this, then A, up, down, then B, up, up, down, then minus, down, C, up, right, D, up, 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 down, plus, then E, then F. Clear? So you can easily get prefix once the arithmetic expression is coded in the binary 3 expression, arithmetic expression 3. Now this is pre-order. You also have in-order traversal. Now in in-order traversal, notice that this visit, instead of here, now you move to the middle. Okay? The rest are the same. Just cosmetic different, the name in order, in order, in order. See? Clear? Now in order, notice that you must visit all the left children first. Children means great grandchildren, grandchildren, great grandchildren, and so on. Okay? All the left side must be visited. So for example here, I cannot visit 6 because the left side are not visited yet. Go to the left, I cannot visit 4 because this one not visited yet. Go to the left, I cannot visit 2 because this one not visited yet. Okay? Go down. And now I can visit number 1 because number 1 technically has no left. Clear? Then go up, and now only I can visit number 2 because left side all visited. Then go to the right, no left, visit, up, up. So now all left visited, so I can visit 4. Go to the right, visit, up, up. Okay, now all of this visited, so I can visit 6. Go down, cannot visit. This one not visited. Go to the left, visit, go up, and now I can visit this. Down, cannot visit. Left, visit. Right, visit, visit. Done. Okay. Clear. Cannot visit. Up, visit. Right, up, up, visit. Now E, because it's not left, I can visit. Visit, up, 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 visit, down. This F, down. This not left, can visit. Visit, up, up, visit. Done. Clear? Now there's another way to get this. for in order only. You can use what is known as in order by projection or by squishing technique. If you arrange this properly, okay, then you can read from left to right. You will get the same answer. Okay, same answer of your in order traversal. Clear? And once you perform in order, the result will be similar to the one that you are familiar with, because it's in order will result in infix. Clear? Now, if you're not comfortable, you still want the bracket, you can put this, okay? So we can put the bracket before the operand, but not all operand. Okay, I don't want to have the bracket at A, for example, or at B. No purpose. So I will only take the one that is not a leaf node. Okay. So if it's not a leaf, we add opening. If it's not a leaf, we add closing. And then you have post-order traversal. Now notice here, in post-order, you need to visit all the left and all the right. It means, once you enter, you cannot visit 11 until you have visited all of this. Clear? Okay. Go to the left. I cannot visit 5 until I have visited all of this. Go to the left. So I cannot complete that. I cannot visit that until I have completed this. Go to the left. There is no children. So that is my first visit. Go up, cannot visit because of these two. Go down, visit. Go up, visit. Up, visit. Sorry.
Is the same thing like pre-order?
No, this one you must visit all the children. Okay. So from here, when you go up, you cannot visit this. Okay. Go to the right, visit. And now only I can visit this one. Clear? This is post-order. Pre-order, when you come, you visit automatically. Straight away you visit. This one, when you come, you cannot visit until all the children visited. Okay. So it's totally opposite of pre-order. Up here, see, you can see I cannot visit this. Go down, cannot visit this because this one not visited. Go to the left, visit. Go up, still cannot visit this because of this. Go down, cannot visit. Left, visit. Up, right, visit. And now I can visit 9. Now I can visit 10. Now only I can visit the root. Clear? Any question? Any question? Now you see the code, same thing. So from here, you just put the visit at the bottom. Just change the name to post order. Done. Okay, cannot visit, cannot visit, cannot visit, visit. Up, cannot visit, visit. And now can visit, up, cannot visit, visit. Up, visit, up. And now can visit this. Up, cannot visit, visit. Up, visit, up, visit, up, visit. Okay, clear? So if you run post order on expression 3, automatically you will get postfix. Okay, clear? Now this pre-order, in order, and post order are example of depth first traversal. Okay. Now we call depth first traversal because you go deeper and deeper and deeper and deeper and deeper and deeper. Clear? So it's basically you go vertically down. But there's another way to navigate this by using level order traversal, also known as breadth-first traversal. Okay. Now in level order, to navigate this, you just go left, right, going down. That's it. Very simple. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So it is very simple for us to navigate this, but it is not so simple for your computer. Okay. So if your computer want to do this level order, you can see the code that's needed is a lot more. You need to put inside the queue and so on. Okay. So this is another example, something that's easy for us but not easy for the computer. Okay. So that's why when we navigate a tree, normally we use pre-order, in order, or post-order. Okay. Now another thing that your binary tree can help us is the searching. Now remember the problem of your linear search. Okay, and then we improve this using binary search. Binary search is very fast because the list is sorted. Okay, so the list is already sorted. So when you search, you can go to the middle, and then go to the middle, go to the middle, go to the middle, and eventually you see your items. Okay, but because the list is already sorted, the searching is locked to n. The problem with this is the sorting part. Okay, so sorting is often n squared. Okay, so that's the problem. And then even if I've sorted this, let's say if you have new data coming in, I still need to check one by one to put where to find the position for this new data. For example, the new data is 80. So it will go all the way up to near 80 in order to put or to reserve the slot. Okay. So the searching is actually, the insertion is actually O n. Okay, so you go one by one. So you can see, I did not get the actual log to n benefit. Okay, in this case. But if you use binary search tree, now it's different. Okay. Now in binary search tree, notice that this is already sorted. Okay. It doesn't seem like it is sorted. Okay, the way that we normally see a sorted list, but this is already sorted. Everything on the left side is lesser than this number. Everything on the right side is greater than that number. Anything lesser than 6 is on the left side. Anything greater than 6 is on the right. Okay. So the tree is sorted. So what happened when you search something? Let's say I'm searching for number 14. Okay, 14. So you go here. 14 is not 8. 14 is bigger than 8. So you go to the right. Once you go to the right, half of this is not important anymore. Okay. So when you go to the right, because 14 is bigger than 10, you go to the right, and then you get your items. Okay. So you can see here, this is very similar to your binary search. You cut into half, you go down, cut into half, go down, cut into half. Left or right. Okay. So the searching for your binary search tree is the same, log to n. But where this binary search tree shines is the sorting part. Okay. Now in binary search tree, when you insert, you don't simply insert anywhere. Okay. So when you insert, you need to insert at a proper place. So that once you have inserted, the list is already sorted. Okay, so for example, I want to add number 9. Okay, number 9. So when you insert, it will compare with 8, and 9 is greater than 8. And it's not possible to have duplicates, it's primary key. So it will go to the right, and they will compare with this value, 9 and 10. 9 is smaller than 10. So it will go to the left, so 9 will be here. Clear? Okay. So once you put 9, notice that everything is still sorted. Okay. And when you insert something, it's the same like you are searching. Because 9 is greater than 8, you will not see this anymore. Half. So the insertion for your binary search tree is log to n. The searching is log to n. So overall is O log n. Clear? So that's the reason why you find that in most cases we don't use binary search. Okay? Instead, we use binary search tree. Clear? Any question? Any question? 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 Clear? Okay? Okay, you can take your short break. Come back at 4:50.
It's the same.
Okay, let's continue. Now let's see the code for this binary search tree. Now there is this binary search tree code, VST code, and I've copied this and pasted in this program. So what we will do is we will replicate the tree that you see here. Okay, so we reconstruct this tree. Now remember, if I want to reconstruct this tree, my root need to be number 8. Okay, cannot be any other number, it has to be number 8. Because if I take other number, let's say for example I take number 3, then after that, if it is number 13, then 13 will be here. Then if after that is number 6, 6 will be here. Clear? You will not be able to replicate this tree. So if I want to replicate this tree, my root must be number 8. And I need to put in certain order. So after 8, I need to put number 3, and then number 10, and then number 1, number 6, 14, 4, 7, 13. Then only it will reconstruct this tree. Clear? So it's basically something like your linked list, but it has 2 pointers, okay? Left child and right child. And inside you have a key. Now remember, this is a key, meaning it has to be unique, not data. Okay, if data you can just put any data, but key must be unique. So first, I initialize the root and put number 8. Okay, so time node will point to whatever it's pointing to, and then you initialize the key left child null, right child null. So essentially what you are doing is you are creating the first node, key number 8, left child, right child. So left child point to null, right child point to null as well. Clear? Okay. So that is init VST. Okay, now we start inserting the number. So let's say number 3. So we call insert VST, which is this one. Okay, insert VST. So the key is 3. And then here we say node is root. Okay, so basically your node is whatever root is pointing to. So this is node. So node is pointing to this node. So the first thing that we will do is we will compare the key. See whether it's smaller or whether it's bigger. Now it is not possible for the key to be equal because this is unique. So it's either lesser or greater than. Now in this case, we are adding number 3. So when you compare with the key here, 3 is smaller than 8. So it will go to the left. Okay, which is this one. It's smaller. Clear? Then you check whether the left child is null or not. This one, not arrow left child. In this case, it happens to be null. So it's true. So meaning this is not true. This one if it's not null. So because it is null, you will do this. So what is this? Creating a new node and set the left and right child equal to null. So you create new node, key number 3, left child null, right child null. Clear? Then node arrow left child equal new node. So node arrow left child, which is this arrow, equal to new node, which is this arrow. So automatically you are creating this link. Clear? Okay. Now what happens if we add number 6? So 3 is done. Now we add number 6. Now 6 is lesser than 8, so 6 will go to the left, meaning you will execute this part, left side. Then you check if the left child is null or not. Okay. Now in this case, the left child is not null. So because the left child is not null, you will call insert VST. So what is insert VST? Insert VST. This is recursion. Okay, it's calling itself. But when it calls itself the second time around, notice that you are not passing root, you are passing node arrow left child. So meaning here, you're passing this node, not arrow left child, and this become your new node. Level 2 is level 1, this is level 2. And then you do everything all over again, same thing. You check whether it's equal or not, or you check whether it's lesser or greater than. Now, number 6 is greater than 3, so it will go to the right. So now it will go to the right, it will go here. And then you still check whether the right child is null or not. In this case, the right child is not null. The right child is null. So because it is null, you will do this. You will create the node. Okay, so you create a node, key 6, left null, right null. Then you set node arrow right child equal to new node. So node, now this is node arrow right child equal new node. Automatically it will create this. Done. So that's basically how the insertion is done, okay, using recursion. But how do we verify that this is correct? How do we certain that we have built this tree? So in order to do that, I need to do searching. Okay. So let's say if I search for 14, then on the left side I should get 13. On the right side I should get null. So let's search for number 14. So number 14. Now notice that once I manage to find what I'm searching for, I'm not interested in this number because they're searching for 14. So why you need to return 14? Instead, I'm interested in knowing what is on the left and what is on the right. Okay? So to do that, I need this pointer pointing to 14. So I will return a pointer. Okay, so I will return a pointer. So that's why you see this pointer created, and then you search BSD, equal to search node. So search node is the pointer that you return. So this is the search BST. Now for this search we use time node. So meaning when you start, this is your time node. Okay, and then you check whether it's null or not, whether it's complete or not. Now if the key is equal, now you're searching. So if the key is equal, this one definitely not. You're searching for 14, this is 8. So not equal, so you will do this. So if the key is lesser, it will go to the left. If the key is greater, it will go to the right. Okay, in this case, because the key is greater, it will go to the right. Okay, it will go to number 10. And then notice that you run search BST, meaning you run this again. Recursion. Okay, now you're in the second level. And then you pass time node arrow right child to become your time node. So now this is your time node level 2. Level 1, level 2. So that's done. You go up and again you check whether it's the same or not. So definitely once you go down here, this one is the same. Okay. So this is your time node 3. So once you find your matching, notice that okay, you will return time node. So you will return this pointer. And you will return that pointer to search node. So inside search node is this pointer. So because I have access to this, I can see the left and right content. Okay, then I check. Okay, if left child equal to null, I will print null. If it is not null, I will print whatever inside the key. Same with the right child. If it's null, I will print null. If not, I will print the content. Clear? So here, you will print left to the 14, which is 13, and right to the 14, which is null. So when I run this, you get 13 and null. Clear? Now if I search for number 6, I should get 4 and 7. Six, 4 and 7. If I search for number 1, I should get null and null. Null and null. Clear? So that's basically how you use binary tree. Any question? Any question? 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 So using binary search tree, I can get a very fast sorting, because when you insert automatically it is sorted log to n, and very fast searching log to n as well. Okay, but there's a problem with binary tree, binary search tree. So what is the problem? What is the problem with binary search tree? What's the problem with binary search tree?
The problem. Where is the problem if I is 3? What is the problem? What is the problem if I is 3? Sometimes you cannot find the middle. Find the middle? What do you mean?
There's only 2 children.
Now, let's say, for example, this is our example. Okay, remember just now I put number 8 as the root. Now, what if instead of number 8, the first number that entering this tree is number 3? So now 3 becomes the root. And what if the next number is number 4? So you put on the right side, right? And then the next number that comes is number 6. Now it's here. Then the next number comes is number 7. See the problem? So if I want to insert number 8, how many comparisons do I need to take? Or how many comparisons do I need to do? Not number 8, let's say number 10. Number 10. How many comparisons? If I'm using this, only one comparison, then number 10 will be here. Okay? If I'm using this, I need to check left or right, left or right, left or right, left or right, and then only I put number 10. So I need to compare 4 times. So there are 4 items and I need to compare 4 times. This is O, N. Now it's not really log to N anymore. Clear? What if you want to search? I want to search number 10. So I will go here, number 10 bigger, number 10 bigger, 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 and now I reach number 10. How many comparisons? Same thing. So you get O, N as well. So although theoretically this is the O log N is the insertion and O log to N is the searching for your binary sort, binary search tree, it is possible that you will get ON plus ON. If the tree is not balanced, it's skewed either to the left or it's skewed to the right. Okay? So you only get the benefit of PSD if your tree is balanced. If the tree is not balanced, you can see it's more like ON rather than O log 2N. So how do we solve this? How do we solve this? What needs to be done? The problem is the tree is not balanced. So to solve this, you need to make the tree balanced. Okay? Now there is such a binary tree that can balance the tree all the time, which is AVL3. Now, so the problem with the normal tree, normal binary search tree, is really depend on the sequence of your keys. So for example, this is the sequence of my data that coming in. So the result of this is this tree, not this nice binary tree. Okay? So I don't get the benefit of log 2n. But if you use AVL3, it will always ensure that your tree is always balanced. Because what will happen is, if it detected any imbalance, automatically it will balance itself. Not balanced, it will balance. Not balanced, it will balance. If you insert, it's already balanced, nothing needs to be done. But if you detected there is imbalance, it will balance itself. So ABL3 will constantly balance the binary tree. Clear? But you can only do this ABL3 only if you start from the very beginning. Clear? If this already started and this is your tree, you cannot make this as ABL3 anymore. Too late already. Okay? So if I want this ABL3, I must start from the very beginning, meaning from the first key itself. And then only I can use ABL3. Clear? Now we will look into ABL3 in your next tutorial. Okay? Meaning next week. Remember your next class, which is the lecture, we will use that time for our midterm feedback. Okay? So where you can check your paper next Tuesday. So your next class technically will be next tutorial. Any question? Any question? 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 Okay, today is the last time where you have your subgroup meeting in class. Okay. So go into your subgrouping. (23A), (23B), (24A), (24B), (25A).
8个小时，就是花了很多精力，尽量的说，there's one of the challenges with the finding guide of is one of the significant milestones. This language brings out all the ideas. But don't put and don't call it something read about services. 是这是是的意向不同的相关的思想，也是的，因为上面的这样的习惯，不能是，这块也是这样的，一个上面，我there was one thing. Yes, you got to do this. Then I did my part. But we are discovered that and all on city bonds is from 6 to 4 weeks. That's what is but this is